everybody can hear you.
Let me see. Yes, I can see you.
Okay, we can start, so please.
May I ask you to put screen a little higher because, or so that it will fit image, or you see it?
Okay, let's see.
Okay, if you see up to, because part of screen is invisible, it seems to me. But
could anybody confirm below the part in the bottom is visible?
The Institute for Advanced Study, Princeton, yes, it's okay.
Yeah, yes, okay.
Oh, okay, yes, and at the top also, because some figures will be very big. Okay.
Yes, very beautiful.
Yes, maybe you can, it's very bad that I will be speaking, telling next slide, but it's okay. It's like in my childhood. Okay.
Hello?
Okay, Professor Ruffini, you are moderator, so please, you can proceed.
Well, good morning, everyone. It's a great pleasure to have Rashid Sunyaev of the Space Research Institute of Moscow, of Max Planck Institute for Astrophysics and the Institute for Advanced Study of Princeton to deliver this lecture about the result of the first all-sky survey and plans for the future of the Russian ART-X and the German eRosita X-ray telescopes. And it's a special pleasure because, as everybody knows, Rashid has been one of the closest collaborators for many years of Yakov Borisovich Zeldovich. Please, Rashid, start.
Yes, thank you very much, and many thanks for inviting me. And I saw the list. I don't know how many people are hearing me now, but there are names of people whom I knew for many years, and I'm glad that at least their names are on my screen. Please, next slide. Oh, Gregory. Oh, yes. I should return to 1987, when in Moscow, very broadly was celebrated the 30th anniversary of the launch of the first Sputnik, of the first man-made apparatus to the orbit. And a lot of scientists from abroad and from Russia were invited to international meeting in Moscow. And it was announced by Intercosmos that it's possible to bid for the mission with very broad international collaboration, which will be launched to the orbit by Russian spacecraft will be produced by Russia, and also the launch will be Russian. And among people who very strongly supported my proposal at that time to launch the X-ray mission were obviously my mentor Yakov Zeldovich, was Andrei Sakharov, and were a lot of people whom cosmic ray community, for example, knows very well, like Zatsepin, Chunakov, a lot of well-known Russian physicists. I can tell you that the letter for us, 26 people signed it to support proposal of X-ray mission, and obviously Ralph Sagdeev, IT director at that time, also was supporting. Two missions won. This was Radioastron, proposed by Nikolai Kartashov, and our mission, which was named Spectrum X Gamma, because we wanted to install the X-ray and gamma ray devices. Please, next slide. And during 1987-2003, a lot of countries joined this effort. You see here the list. First time USA was joined, and relations with Israel were practically non-existing, but nevertheless it was possible through Denmark include also Israeli device. And everything was okay, and you see huge image of huge spacecraft, which many devices were ready to fly. This device, there is a device, I don't know, do you see my where I'm showing, but there is small second telescope, joint European X-ray telescope below the main SODART. And this telescope is in reality now, yes, it is now flying on American many years successfully. Its duplicate is flying on American spacecraft Swift. But as you know, around 2000, there was drama for not only for our project, but there were great changes in the Soviet Union. Mission was delayed and canceled when many devices were ready to fly. We were trying to fight for continuation of the project, but top people in the space industry told me, Rashid, country became practically twice smaller, and in population at least, and therefore your mission also should be smaller, but we will try to keep it in the list of possible missions. Please, next slide. On this slide, you see now the final result of these negotiations. It's already spacecraft ready to be launched. And from instead of a lot of different small and big devices, we went to very clear scientific task to scan the whole sky and to get a huge amount of extragalactic objects, for example, 100,000 clusters of galaxies, most massive objects in the universe, and to observe all of them, the massive clusters within horizon. And this amount of these clusters was 100,000, and we were looking for group which will be able to create such an instrument. And this is this instrument. Finally, Günther Hasinger and Peter Predel helped us to finally, there were very long negotiations. They were proposing small device which would be able only to observe a few thousand clusters. But we were telling no, 100,000 and millions of supermassive black holes. And the result is this device, eRosita. Andrea Merloni, now PI of this instrument, will tell us much more. We decided that it is impossible in half an hour to tell everything about spacecraft. But for you, I can tell you that Russia launched this spacecraft with Russian instrument ART-XCX and eRosita onto the orbit around L2 point of the Sun-Earth system, a Lagrangian point. I will show the map. But for you, I can tell you that total mass of eRosita is 808 kilograms. It's a huge device. And you see here people and dimension of telescope. Telescope is 3.5 meter in length and 1.9 meter in diameter. It's a huge instrument. Similarly big is ART-XCX. This is X-ray telescope. It is staying here. And on the right, you see the navigator platform. This is standard, now standard platform for Russian scientific and meteorological spacecrafts, and developed and produced by Lavachkin industry near Moscow. And this is, we told that this is SRG spectrum, RG X-ray Orbital Observatory. You see it. Please, next slide. This is a launch. There was great day, July 13th of last year. It's more than a year ago when huge, but biggest in reality now, the Russian launcher Proton from Baikonur site in Kazakhstan was launched, and its power was not enough. There is to carry this spacecraft. There is also booster D3M, which helped us to reach without maneuver around Moon, just directly L2 point. Please, next slide. On this slide, you see the projection of the orbit of spacecraft to the ecliptic plane. Sun is here at 150 million kilometers from the Earth. This is Earth in Russian. And this is orbit around is the orbit of the Moon in the middle. You see, yes, this is 380,000 kilometers radius. And this is L2 point where gravity and centrifugal forces of the motion around Earth and Sun, they balance each other, and therefore there is a quasi-stable point where a lot of astronomical spacecraft are working. And we were flying several months there, and now we are making already second tour around this L2 point, and every tour is of the order of half a year. And during half a year, spacecraft is rotating. We are scanning the whole sky. Please, next slide. This is again, I show you this eRosita, this ART-XC. Please, next slide. And this is ART-XC device. It is Vulture type crazy coincidence mirrors. These mirrors, 7 mirrors you see here, are supplied by the Marshall Space Flight Center, where Werner von Braun was working, as you know. NASA produced it. And these are collimators, and then 7 detectors which were produced in a key. And this also is very big device, but its energy range, I'm telling you, is 5 to 30 keV, when eRosita is sensitive from 0.3 to, let us say, 8 keV, but in reality, what I will show you today was obtained from 0.3 to 3 or 4 keV only. Therefore, this is, yes, field of view here is huge of the ART-XC. It is 34 arc-minutes, but I can tell you also that eRosita has 1 arc-minute, 1 degree field of view. Yes, and this device, it has also excellent time resolution, better than 1 millisecond, in reality 23 microseconds. Please, next slide. On this slide, you see the dependence on effective surface area of 2 devices, eRosita, ART-XC, and there is green. This is the American spacecraft NuSTAR, well known. You see that eRosita dominates at rather low energies of X-rays. In reality, it's working from 0.2, 0.3 keV up to this jump of sensitivity around 2.3 keV. It's working well, but ART-XC is working well up to 30 keV, very well, and it's comparable in its sensitivity to American NuSTAR. Please, next slide. And this is just comparison. NuSTAR has very narrow field of view. And this is a mosaic of images of the galactic center. You all see Sagittarius A star. This is our black hole. And this is 144 kiloseconds of exposure of NuSTAR. And this is what ART-XC sees in 4.8 kiloseconds. The image of the same sources. Yes. It's pity for me, I will mention today many times slides made by Mikhail Pavlinsky, who was PI of this instrument. Mikhail Pavlinsky, unfortunately, he was my deputy on this mission, and unfortunately he died when he was 61 years old, and this was also a great loss for us and for our mission. Please, next slide. Yes, this is on this slide. You see, if you yes, you see the pulsation of the pulsar, beautiful pulsar. It is green here. If you knock, if you push button on this screen, there will be motion of this green arrow. No, previous slide, please. Yes. Okay, doesn't work. You can see here the green, this is pulsar, and this is huge nebula created by the wind of relativistic particles from this pulsar. And you see shocks and so on. All this sees, all what is green or gray is observed by ART-XC, and distant shock at very low energies was observed by Chandra, but eRosita also sees it. This is good timing. You see how well we see the profile of this pulsar. Please, radio pulsar. Please, next slide. Now I show you the images, deep images of SRG eRosita. We got these images during flight to the L2 point several months, and we were pointing to places which are of interest for a broad community. This is 20 square degrees field in the galactic range, 20 degrees away from the galactic center, but in that direction. And it's very heavily populated region. You see here point sources. This is thousands, many thousands of X-ray sources, mainly stars, white dwarfs, everything is galactic, but maybe 20 or 30% of all these point sources, which you see here on the image, are quasars, which are very far, but we see them through our galaxy, through the body of our galaxy. What objects most interesting you see on this image? First, there are two supernova remnants. You see here at the bottom, one of them, supernova remnant, and they are well known. And another one, green. Green, there are three colors, green and blue. These are high temperatures of the order of tens of millions Kelvin. And red, for example, this is temperature lower than 1 million Kelvin. And you see here different, this image gives you this understanding. There is pulsar, you see blue, it is not blue-green, which is also very bright. There is ordinary star, you see here, star, and it is rather close to us. This is T-Star, a very young star, which we also see here, and it is bright in X-rays. And here you see the cluster of stars, newborn stars in the star-forming region. We see all this beauty. I told you there is even cluster of galaxies. I forgot in which corner is it. But for astrophysicists, most interesting is this diffuse matter. You see these red regions, green regions, and gray. And this is gas, hot gas, which was heated by very old supernovae, and it fills 90% of the volume of our galaxy in its plane. You know about molecular clouds, which are very cold, 2000 Kelvin. You know about hydrogen, neutral hydrogen, 21 centimeter line emission, which has also temperature of the order of 100 Kelvin. And here we see that 90% of the volume of our galaxy is filled. This is well-known theoretical work of interpretation was written by Jerry Stryker and Chris McKee long ago. And now we see this gas everywhere, this hot gas. Please, next slide. And now I show you the main result of our mission. And this result is a map of the whole sky. You see it here. This is the best map of our universe in the X-rays. We see here a little more than 1 million of point sources You see here many small points. It's impossible to show on this screen a million, really, whole million of the sources. But you know, if you will make this image maybe 30 meter to 30 meter, you will see many of them. Amount of pixel will be enough. This plane you see here in the middle, in equator, this is the plane of our Milky Way. And you see that it's in many places it is dark because there is strong absorption of soft X-rays by cold interstellar gas. You see it. We see it mainly not in emission, but as in absorption. And you see here much more objects. These are well-known black holes in binary system like Cygnus X1. We see a lot of neutron star, neutron stars. We see Crab Nebula. We see huge systems of the supernova explosions. This is our galaxy. But most interesting is the beautiful image you see of giant explosions in the center of our galaxy due to multiple supernovae, but also I'm sure this is the result of activity of our central black hole, which has mass of 4.4 million of solar masses, and today it is dormant. But we know now that 100 years ago and 1,000 years ago and million years ago, it was enormously bright and it expelled a lot of matter and a lot of cosmic rays. You heard about, but it's well known because these features around are observed now also by Fermi spacecraft. But here you see beautiful, huge traces of explosions in the central part of the galaxy. Nobody before had so beautiful picture. Even some of the images were observed by German Rosat spacecraft. PI was Erwin Trümper. This is the same group which created eRosita in Max Planck Institute for Extraterrestrial Physics. Please, next slide. And here I am writing you that what's Peter Predel, PI of this instrument, sent me several months ago. You see here that first sky survey by the Spectrum RG satellite allowed the eRosita telescope to construct a map containing almost 10 times more, I think, more close to 5 times more X-ray sources than the former world best map of the German satellite Rosat obtained 30 years ago. And 30 years ago, thousands of astronomers on the world were using maps of Rosat. We hope that our maps, when we make 8 such pictures, each is half a year of observations, and add them together, we will be maybe 50 or 80 or 100 times, we will have more sources than Rosat had. And this is very important. There are many nearby stars with stellar coronae, which are hundreds and thousands times brighter than corona of our sun. Star-forming regions, a lot of different things on this map. You can see a lot of neutron stars, enormous amount of white dwarfs, 200,000 objects of stellar origin, and Gaia spacecraft permits us immediately to separate nearby stars just due to the proper motion or parallax. But 3/4 of the objects here, 750,000 on this map, are distant quasars and active galactic nuclei, powered by accretion or you are astrophysicist and physicist and know that this inflow of matter onto supermassive black holes residing in their centers. They are far beyond the Milky Way at distances of hundreds of millions and billions of light years from us. And such maps, when we created it, when we detect not 750,000 quasars, but several millions, 3 or 5 millions of these objects, then we will be able to trace how these black holes were growing, when they appeared in our universe. We can, using optical data, we can measure when they were born. Please, next slide. Here, this is a standard picture why the black hole cannot radiate itself, except Hawking radiation, but this giant, it's negligible, giant black holes. These are black holes which we are observing with masses millions and even billions of solar masses. There is angular momentum, everything is rotating, you know, there is friction, this normal theory of disk accretion. And this gas, due to turbulence, is disappearing and heating the gas, and we see very bright X-rays. In many objects like blazars, relativistic jets contribute to X-ray luminosity. It's very interesting, and these are very compact objects because these are, even with huge mass, you know, now observations of M87, radius is in relative measure of the photosphere. Here, we know that a lot of X-rays are coming maybe from distances several times higher. Please, next slide. I can tell you that our dream is to measure baryonic acoustic oscillations just using this sample of our quasars. We dream that this will be done 2024. It's important to survive. We think that more than 3 million AGNs will be detected, and it will be possible to see at 10 standard deviations the baryonic acoustic oscillation in their distribution on the sky. We need optical follow-up to measure redshifts, but today new methods like machine learning, neural nets, they permit to use all information about this existing information about quasars and calibrate the photometric data. And in principle, this precision is not very far from achievable already with data which are existing due to such a great instrument like Sloan Digital Sky Survey, or for example, JPass, which is working now with 56 filters in optical band in Spain. Marat Gilfanov computed this, modeled, and there are interesting data. Please, next slide. Yes, and it's very important that we finished first our sky survey more than 2 months ago. But now we are performing the second sky survey. I told you that we dream to have 8 of such sky surveys. Each has duration half a year. More than 33% of the sky is observed now second time. And we can compare old map and new map with time delay half a year. And this gives us information about variability of 100,000 of X-ray sources during half a year. There are many tens of sources which we already detected. We changed their brightness during half a year more than 10 times. What is the reason? And we are looking first for gamma ray afterglows, but especially interesting are tidal disruption events. Please, next slide. And here you see the picture made by Eldar Habibulin. You see the star, which is going, and then it's around very close to supermassive black hole. And at some distance, the density of matter in the star becomes smaller than density or average density of black hole in the whole at the distance of the orbit of this star. And in this place, tidal forces can disrupt the star matter, and star disappear. It is disrupted, and you see part of matter is going to infinity, and another part is captured, forms the accretion disk, and on the sky, very bright, you see on the right side, this is the duration, very bright source appears up to for the time of the order of 1 year. And I told you that we can measure every changes of the 400,000 of objects on the time of half a year. We are doing this now. Please, we are looking for such objects. Please, next slide. Here I show you, for example, this is 25% of the sky when it was observed during the first scan. I did not create a new picture, but we have very, very similar picture now. And you see here huge, this bright object here, it is star formation region in Cygnus. And you see the dark region, it's galactic plane where soft X-rays are absorbed. And you see here also, this is a small region where we see the very bright galaxy cluster at redshift 0.08, cluster of galaxies, and quasar in vicinity, which has redshift 2.7. And this is the image of the same region obtained by Planck spacecraft. I can mention again name of Zeldovich. You see how bright and bigger is this cluster of galaxies in the microwave band, because this here you are measuring in a Z effect, you are measuring it's proportional to the density of the gas, and you are sensitive also to the outer regions of the cluster. And in the X-rays, it is mainly Bremsstrahlung, and due to the collisional project, you need everything is proportional to an E-square. Therefore, object seems to be more compact. Many objects of galaxy cluster which we are observing, and we observed only during sky survey 16 or 20,000 clusters of galaxies already. It's enormous how many new clusters we are observing now, clusters of galaxies. And please, next slide. I can compare this picture with previous. This is our deepest sky survey. We spent a lot of time on during the flight to the L2 point observing Lockman Hole. Lockman Hole is well known because when Lockman was very young, he is working in 100-meter dish in Green Bank. He observed sky in the 21 centimeter line and found the place where the amount of hydrogen, column density of hydrogen, is the smallest. Therefore, in this region of Lockman Hole, we have the smallest, weakest absorption of X-rays. And we see here on this region more than 8,000 objects. Majority of them are, again, quasars and active galactic nuclei. And there are, in this region, more than 100 clusters of galaxies. We can work with this very deep, and I can tell you that we are discovering now quasars. For example, we see the object, and this is a quasar with redshift 6.19 or 547. We are telling to optical astronomers, they measure the redshift, and there are many records. I think that we already in optics confirmed, although not confirmed, measured redshifts of 30 quasars with redshift significantly higher than redshift 3 and more than 10 with redshift higher than 4. And we continue, and this always done not with very big telescopes. Please, next slide. Yes, this X-ray image of coma cluster in hard X-rays obtained by ART-XCX telescope from 4 to 12 keV. There is also a beautiful image of the same cluster in soft X-rays by eRosita. We will publish it soon. But around in this field, you see a lot of clusters of galaxies in similar field, which are at redshift 0.4, 0.5, up to 1, just around Coma cluster, which nobody was seen because Coma cluster itself very bright, but we see now with eRosita this easily. And this is Planck, how it sees it in microwave in the band of cosmic microwave background. And again, object is in microwave bigger, and here majority of distant objects which we are observing. They have their diffuse for us, but the angular dimensions are of the order of 1 arcminute. Please, next slide. Yes, why clusters are so interested? This is propaganda, very old propaganda slide of Eugene Churasov from NPA, and you see amount of clusters, you see per megaparsec cube at different redshift. Red is in our vicinity, blue is at redshift 0.5, and green is redshift 1.4. And you see how strongly amount of rich clusters of galaxies with mass in dark matter, 10 power 15, 10 power 14, how it rapidly decreases with time and with mass. There is very small amount of clusters with 10 power 14, but majority of clusters which we see are here. These are massive clusters. There are only 100,000 in the horizon, and we are looking for them and studying them now. And I told you that we already detected of the order of 15 or 20,000 clusters of galaxies. We are checking these are really these diffuse. All these diffuse sources are clusters of galaxies. It's very interesting. Just observing them, counting them, you can see how large-scale structure was growing. It's possible to measure cosmological parameters. It's really great science. And with sample of the order of 100,000 objects, we can do a lot. Please, next slide. Yes, I told you already what are the masses and so on. And we dream to detect all massive clusters of galaxies in the observable universe within horizon of the order of 10 billion years after 4 years of all sky survey, adding together 8 maps of the type I showed to you. And it's pity that Zeldovich left us in '87. It will be a pleasure for him to see these results. Please, next slide. And I can tell you that thousands of people were working in Russia and in Germany to create this telescope, but most important, space to make spacecraft, this navigator platform, and who are working with us, and I'm enormously grateful, who are working with us every day during more than 1 year. We are on the distance on 1.5 million kilometers. Therefore, the biggest giant antennae of the Russian deep space network in Bear Lakes near Moscow, 64 meters, and Tussurisk near border of Russia with China and North Korea. It's really far east, not far from Vladivostok, 70-meter diameter. They're working with us practically every day for 5 hours to sending commands and to dump down the scientific data. And there are people in Max Planck Institute for Extraterrestrial Physics in Garching who are every day checking that telescope is, how to say, in good shape and sending commands how to work even better. The same are people in IKI who are responsible in Space Research Institute in Moscow, who are responsible for receiving all data from industry and who are distributing them, this data afterwards and to the among scientists. It is great observatory. We are very lucky to and happy to report that till now everything is working well, and we hope to work 4 years in this already more than half a year gone, but we hope to work additional 3.5 years scanning the sky, and then our observatory will be working in the point mode, and we will observe most interesting objects which are discovered. Yes, thank you very much. I think that Andrea Merloni will tell much more about science.
Thank you very much, Rashid. Extremely, extremely impressive. Not especially in this moment in which we have so many problems, social and problems in health and everything. This is a splendid example of international collaboration all over Asia and Europe, and giving fantastic view out of the Lagrange point of our universe. What I have been very impressed is the number of the quality and the number of observation, and the very interesting fact that you are planning the following sky survey of the entire 400,000 objects, going from black hole to active galactic nuclei, which we discussed so many times with Zeldovich, but you have been driving through the enormous difficulty and reaching unique success for dimension extension of science and extension of science and a fantastic result. Leading the human people to observe the evolution in real time of our entire universe. Thank you so much. Let's see if there are questions.
Remo, before I can tell you and to people from ICRA, if somebody is of your collaborators also is hearing this report, we are looking for afterglows from gamma bursts, which are not directed to us. You understand me? Which are shining gamma ray bursts in different direction, but we can see afterglows which are more have more broad indicatrix, and it is possible for us to detect now these afterglows, and this maybe will be new great information for the gamma ray bursts.
Of course, because you are looking in the X-ray of the afterglow, but of course the great excitement today is also for looking at the high energy, because while the afterglow is very, very important to understand the evolution of the new neutron star, the high energy is also very essential to see together the action of the black hole emitting jet. Therefore, very, very exciting, and we look forward to collaborate with you in any way we can. There is Razmik Mirzoyan, who has Rashid Alievich has shown all sky X-ray picture. One could see a hint of kind of bubbles emerging from the galactic center region. Could you please comment on that?
I think that now I can, yes, Razmik, I think that within a month or two, we will inform you about beautiful results in this direction. but maybe Andrea will tell more than I can say today. But it's very, very important question.
Okay, we look forward to further news. Razmik, thank you. Thanks you. Okay, if there are no other questions, let's proceed further. And again, Rashid, thank you so much enormously. And we look forward also to next year for a Grossman meeting if the general situation will allow. Thank you again. And
Thank you.
The next talk, Andrea Merloni, Mapping the Hot Universe, the first year of operation of eRosita.
Yes.
Andrea, welcome.
Thank you.
Andrea, my former graduate student, is always a pleasure to see how far he's going and guiding us in the observation of the universe. Andrea, go on.
Thank you. Thank you, Remo, and thank you all for the organizers. I will just continue on the theme that Rashid has so well introduced, but my goal today is to maybe give you some more details about eRosita. I am working at the Max Planck Institute for Extraterrestrial Physics, where the instrument was built and developed. And since about a month, I have become PI of the mission, taking that position from Peter Predel, who has been leading that enterprise for more than 10 years. And so today I will tell you more about the instrument itself, how we operate it, and then at the end showing you some more nice pictures of our early results, which I think are always good to see. So this has already been mentioned by Rashid. The main driver for designing eRosita was cluster cosmology, namely using the number density and the number density evolution of clusters of galaxies as tracers of large-scale structure, and therefore constraining cosmological parameter. In order to do so, we decided, of course, to use X-rays because clusters contain hot gas, which is emitting 1,000,000 degrees gas, which emit in X-rays. And then the design of the instrument came from a number of relatively simple considerations. We wanted to have enough sensitivity to detect a large number of clusters, this famous 100,000 that Rashid mentioned, that are needed for statistical considerations. So for doing that, you need sensitivity. So you need a big telescope, and of course you need to probe large volumes. That's the necessity of the All Sky Survey, to detect the entire population of large cluster along your past light cone. But then, of course, you also want to have a telescope which is good enough resolution, spatial resolution, that it makes easy for you to distinguish between clusters and the point-like population of stars and active galactic nuclei. So the combination of limits, the requirements on PSF and sensitivity was driving the design of our instrument. Here is just a summary slide, and here, of course, I want to mention beyond Rashid, who, as you've just heard, have been pushing for this dream to become reality for many decades now. On the German side, Peter Predel, who was the PI of the mission for more than 10 years from MPE. And I want to mention also Paul Nandra, who is the director of the high energy group at MPE, who together with Peter and Rashid share most of the mission mission leadership tasks. At MPE, we did a lion's share of the work together with a relatively small group of German institutes and universities and industry partners. But at MPE, we not only design the instrument, but we manufacture most of the flight parts. We did the integration and testing of the eRosita telescope. And now, of course, with the strong support from the ICI and Russian ground segment instrument, we are doing data handling, processing, and archiving. Here is a schematic representation of eRosita. eRosita is an assembly of 7 telescopes, identical telescope. Here you see on top the 7 mirror assembly. These are mirrors, and in front of them we have buffer that are being placed in order to prevent stray light for contaminating your images. These mirrors are mounted in this hexagonal structure. Here you have 2 star trackers. You see only one. These are needed for reconstructing the altitude, and so telling you exactly where the telescope is pointing, which is what is important. And on the focal plane, the focus of these mirrors, we have 7 cameras. The camera assembly contain filters. Here you see these dark red filter wheels. The cameras are CCDs that we have developed at Max Planck Institute, and they are governed by complicated electronics. And here you see the radiators and the complicated cables for the cooling system, which are needed in order to keep the temperature of the camera at around minus 90 degrees constantly throughout the mission. Okay, that was the schematic. This is now a real picture of the hardware. Rashid showed you a similar one. Now here you see inverted. eRosita is on top, ART-XCX is on the bottom, the navigator platform here. And this picture was taken in Baikonur during the final integration of the spacecraft onto the rocket. And here you see already the spacecraft is docked together with the upper stage Block TM that brought SRG into this final orbit around L2 that you have already seen. So here I'm going now into the eRosita during construction phase so that you can appreciate also how complicated it has been to build this hardware. Here on the left, you see an image of the mirror side. So the design of the mirror was made to be compact and have a large field of view. This 1 degree diameter that already Rashid mentioned is, of course, very important if you want to cover a large fraction of the sky at the same time, allow you to survey the sky faster. The mirror deliver image quality similar to what XMM does. So one way of doing that is to compute the half energy width, which is the width of the point spread function where half of the energy is deposited, which is about 18 arcsecond on axis. Because our instrument scans the sky continuously, what really matters is the average over the entire field of view of the image quality, which is about 26 arcsecond for the half energy width. This translates into full width of maximum of maybe 10, 12 arcsecond, and that source location accuracy of about 3 to 5 arcsecond, which is in most cases good enough to identify the counterpart at optical wavelength for our sources. This is very important, of course, if you want to know which are the AGN and which are the clusters that we see in our images. As I told you, we spent quite a lot of time at MP to produce buffers that had to be aligned with the mirrors. These are this conical structure that you see in front. They serve as a very good stray light reducer. More than 92% of stray light is reduced. So this would be single reflection onto the Volter telescopes. And of course, if you don't have them, your ability to detect faint extended structures goes up. Here on the right, okay, and then here you see the test that we were doing in Munich before launching the telescope. You see the PSF. So these are image created by moving artificial point source across the focal plane. You see this is very well round at the center of the image, but it becomes quite nasty and distorted towards the edge, and also a bit fainter due to mirror cross-shadowing or vignetting effect. So these PSF maps are very important for us to calibrate the instrument so that we can reconstruct the image as well as possible. On the right, you see the focal plane. Now you see this 7 electronic box, gold-coated electronic box. They govern CCD, which have been developed at Max Planck as an evolution of the PN CCD that has been flying on XMM Newton. So a lot of the technology we use are further development of technology that was developed for previous missions, of course, in particular for XMM Newton. The detectors are extremely good. Here you see an image, let's say a noise map of the detector to see how uniform it is, which of course helps a lot in then interpreting your real source images. They have very little temperature dependence, which is not the case for the XMM detectors. And of course, you see that the entire exposed area is within one single chip. There are no chip gap, no inactive region. We have until now very, very few bad pixels. So the detector are one of the strongest points. And with CCD cameras, each photons that you detect, you can measure its energy. And we can produce spectra of sources when we detect sufficient number of photons. And the spectral resolution of our CCDs are almost a factor of 2 better than the XMM-PN. To give you an idea, a monochromatic line can be, you can resolve the line at 80 eV, so we can resolve 80 electron volt energies at 1.5 kV. This is something similar to what Rashid showed, is the effective area. That tells you how big the telescope is, essentially. The red points are for eRosita, and these are other telescopes. In blue, it's XMM Newton, the largest existing X-ray telescope working now from ESA, led by ESA mission. And then in green, you see Chandra, which you all know is the NASA flagship X-ray mission, which over the time has been losing due to contamination effect sensitivity and soft X-ray energies. So this is the Chandra at launch is the dark green, and Chandra now is the light green. Mainly, the main message from this plot is that eRosita as a telescope is in the soft X-ray energy range, where most of the clusters emit, is as big as XMM Newton. So it's essentially the biggest or comparable with the biggest X-ray telescope who's been working now. So it's a big machine. And this is another metric. When you multiply your effective area times the field of view, it tells you how fast you can survey the sky. It's called GRASP. And here you see that our large field of view gives us an advantage, so that eRosita is the fastest X-ray survey machine that was ever been produced, a factor of 5 faster than XMM, and a factor of few faster than even ROSAT. Here you see pictorially what I just told you in words. The advantage of eRosita stands mainly in its large field of view. This is a comparison of the eRosita field of view with the size of the full moon, or the XMM Newton field of view, or the Chandra field of view, which is even smaller. Plus, I want to mention one other feature, which is the operation mode of eRosita in scanning. As I will tell you in a minute, we do scanning for the Old Sky Survey, but we can also observe rectangular regions of the sky in this raster scan. So when you go back and forth over almost an arbitrary rectangle, you can design in operation mode. This was a mode which was suggested and invented by Tipoletik in Moscow. We are very grateful for that. And so this allows you to produce images of very large patches of the sky with very good uniform exposure. This is you will see now in a minute how nice this image can come out because of this. This I told you already. Again, beautiful image from the launch. Rashid mentioned that. I again want to thank all the people involved in the operations. On the eRosita side, we do commanding of eRosita from MPE, since lockdown, mostly from home. And despite all this complication, the connection between the operation team at MPE and the operation team in Moscow, both at IKI and Lavochkin, has been working very nicely. Really grateful to all the people who dedicate their time for that. And so we do plan the command of eRosita, then we communicate that with the mission control center in Moscow, and this then get uploaded into the spacecraft. And then, of course, we receive data from the spacecraft, we check the health of the instrument. And so every day we have a view of how issues may be arising, and we try, of course, to react as fast as possible. One important point is that being the first X-ray telescope in L2, we are the first to sample the background in X-rays at L2. A couple of points for the X-ray experts in the audience. Here you see the spectrum of the background, a cosmic background estimated in black, and in blue, the actual measure when you take into account vignetting as a function of energy. And in red is the background that you measure in the detector when you close the filter. So you don't expose the sky. This is just due to the particle interacting with your instrument. So this is the instrumental background in red. And in purple, this was the estimate before flight of the level of particle background. And you see that the level is higher than what we were estimating before launch. So of course, this is a negative point. Part of this is due to modeling of the instrument itself, and part of this is due to the fact that we are now working at the minimum, or we have been working mainly at the minimum of the solar cycle, but high energy cosmic rays which interact with your instrument to create this particle background anti-correlate with the intensity of the solar cycle. So we model predict that this particle background will go down as the solar cycle goes up. But the important feature is the background is very stable. Here you see a comparison during simultaneous observation of eRosita and XMM that shows the background in 3 energy range, 0.5 to 2 keV, 2 to 4.5, and 4.5 to 7 keV. The eRosita background is in red, and the XMM background from 2 different instruments is in blue or green. And so you see that the level of the eRosita background is very stable, which of course is very good. That allows us to use as much as possible the observing time. Okay, the first exposure of eRosita. Now I will pass to the final part of my talk with some more nice pictures. This is the first light image taken with the 7 telescope. Now I'm showing the 7 images separately of the 7 telescope. Each of them has slightly different orientation of the camera CCD with respect to the sky. So you see that, these are square, differently oriented. This is a color-coded image. Essentially, we divide the photons coming from 0.2 to 4.5 keV into different energy range, and we assign blue colors to the high energy, green colors to the middle energy, and redder color to the lower energy in this range. When you combine all of this is the combined 7 telescope first light image. You see a variety of sources: background AGN, foreground stars, supernova remnants. This image was taken pointing at the Large Magellanic Cloud, and the bright source at the center is the very famous supernova 1987A, from the one out of which we detect the first neutrino, astrophysical neutrino on Earth. So it's an important field, very famously observed. And in the next slide, you can see a comparison of the eRosita first light image with these beautiful colors and great details with the ROSAT one. ROSAT has a larger field of view, but didn't have CCDs. So we couldn't produce the same spectral information and color information that eRosita. Of course, XMM has a slightly better spatial resolution, but it has a much smaller field of view. And here you see the difference also in the brightness of the 1987A supernova. This image was taken 1990, the XMM neutron in 2000, and this is 2020. And the supernova 1987A has been brightening up over time in this period of 30 years. A few more highlights from the CalPV, means calibration and performance verification. This is everything we did before starting the Old Sky survey. We did a lot of pointings. Rashid showed a very beautiful Lockman hole. Here we see another clusters of galaxy. All of these we have been exposed typically for about 50 to 80 kiloseconds, about 1 day worth of observation. And this image were created to show the very nice picture of a large area of the sky. So this is a clusters of galaxy. This is one of the brightest supernova remnant, Puppis A. Here you see the different energy range again. And this is a system of 3 interacting clusters of galaxy at low redshift. And here we are mapping their interaction region and also detecting many other clusters and groups in the outskirts of this system. And this is, again, the first light image I just showed. One point to highlight the spectral capability of eRosita. If you take the spectrum of the supernova 1987A, here you see the eRosita spectrum in cyan compared to the XMM Newton spectrum taken during the XMM first light. And here you see the advantage of the better spectral resolution of eRosita, all these sharp lines that you can resolve better. And then one point, we did one mini survey. We spent 3 or 4 days to look at the patch of the sky, about 140 square degrees, at the depth expected at the end of the whole sky survey. Rashid said we want to do 8 whole sky survey. As more or less you can expect that at the end of that, every point in the sky will look like this. So in this 140 square degrees, at 2.5 kilosecond exposure, slightly deeper than the final whole sky survey. For example, we detect 400 clusters of galaxy. Many of them have already been associated with optical clusters, so we know that they are at various redshift, 1.1 to 1.1. And we have detected more than 25,000 point sources, including one high redshift quasar at redshift 5.8. And many of these objects now we are following up with optical spectroscopic instrument to measure redshift and characterize this population. But as such, these 4 days of eRosita observation already produced the largest contiguous X-ray survey, just in terms of number of sources detected. So this is another illustration of the power as a survey machine of eRosita. How much time do I have left? I'm sorry.
Some 5 minutes.
Okay, good. So I can show you one animation of how the whole sky survey has been performed, the one that Rashid already showed. This is the SRG spacecraft at the L2, around in the L2 orbit as it scans the sky. That shows how we do the operation. Essentially, we rotate so that in 4 hours, we do 1 circle. So in 24 hours, we pass over part of the sky 6 times. And as the Earth moves around the sun, the L2 point follows it. And so in 6 months, by combining all these great circles, we will have completed the whole sky survey. And here on the right, you see the ecliptic poles coverage and how this coverage get completed as the telescope moves around the sun. So in 4 years, we can do 8 of this whole sky survey, and this is the plan. And as Rashid said, we are now funded at least for 2.5 years more for pointed observation. And there will be time left open for the community to use ART-XC and eRosita through normal proposing. So the first whole sky survey produce very nice images and results. I think Rashid mentioned almost everything that I'm saying here, so I can go quickly. That's the image that Rashid showed before. And this is an highlight of a few known sources. Essentially, all the famous faces, famous name of X-ray astronomy, where, of course, are in this image. Cygnus X1, the first probably confirmed stellar mass black hole. The Crab pulsar is here. The Vela supernova remnant is one of the brightest and biggest supernova remnants in the sky. Here is where the Large Magellanic Cloud is. Scorpius X1, the brightest X-ray sources in the sky, seems extended just because the source is so bright that the wing of the PSF are very, very extended. We have other supernova remnants, but also clusters. The Virgo clusters is here. Coma clusters is really close to the North Ecliptic Pole. North Galactic Pole, sorry. Perseus, Fornax, all famous clusters of galaxies. And even in this image, one of these many point sources, there is one white dot, which is a redshift 3 quasars. As Rashid said, in fact, there are a few more very high redshift quasars that we have detected in the first whole sky survey already. A few highlights, zooming in on these images. This is the Vela supernova remnants, again, false color images in the 0.3 to 3 keV range. That's a very nice complex of actually 3 supernova remnants that appear in projection over the same part of the sky. The Vela is the largest one with the Vela pulsar in the middle. Vela Junior is a harder, younger supernova remnants, which therefore appears round and bluish here. And on the right, another bright supernova remnant is Puppis A. This is again the Large Magellanic Cloud, but now seen through the first whole sky survey. So you don't not only see the central part, but the entire diffuse gas that is generated by generation of supernova remnants in the Magellanic Cloud. This is another nice discovery. One of the things that you discover by chance. You see this beautiful ring. This is a dust scattering echo. So these are X-ray which were produced by an X-ray transient, which is the source at the center. It's a X-ray binary that went in outburst in early 2019. And this source was so bright that we can still see the echo of this outburst through scattering of the X-rays into intervening dust lanes, okay? And by measuring the diameter and the property of this dust echo, we can reconstruct the distance of the X-ray transient and say something about the dust property along the line of sight. So as Rashid said, we are planning to do this for 8 more times to detect all massive clusters along the past light cone. We hope to detect many million active galactic nuclei, and then a plethora of compact objects, the population of compact objects in the Milky Way, the population of young stars in the Milky Way, nearby galaxy and galaxy group will be observed, and also variable like tidal disruption event that Rashid already mentioned. Not, of course, to forget the ability to detect things we don't expect. Maybe we will have new discoveries, and we need to be ready for that. So with this, I will close my talk, and thank you again for the hospitality.
Thank you so much, Andrea, for this beautiful talk. I was reading again by chance yesterday the first discovery of an X-ray source outside the galactic, outside the solar system, by Riccardo Giacconi and Herb Gursky. And this was the starting of relativistic astrophysics. And today we can see, again, SCOEX-1 observed by you, but together with SCOEX-1, they discover to see how rich has been relativistic astrophysics, going to cluster of galaxy, going to million of massive black holes in active galactic nuclei, and also go back in very big, great details about all the sources that we have been studying since. Congratulations again, and let's look forward to further success and continuation. See you then next year from MG16, and let's see if there is any answer, any question. No, we don't have a question, and therefore a very warm thank and congratulations.
Thank
you.
Go
ahead. We go now to Alena Khokhriakova.
Thank you.
And okay, yes.
I think I can't share my screen for a while. The button is not available.
Just a moment.
Please try
Thank
now.
you. Yes, I have it.
Okay, just a moment.
Good morning. My name is Alena Khokhriakova. Can you hear me?
Good.
Everything is okay?
Yes.
Okay. I'm a student of Lomonosov Moscow State University. Today, I will present my study of detectability of isolated neutron stars by eRosita in collaboration with Sergei Popov and Anton Biryukov. I will study with a brief introduction to the problem of this work. Studies of most astrophysical objects can be roughly divided into the study of individual sources, for which there is a lot of data, and the study of very large and possibly homogeneous samples. The first approach allows, as a rule, to check in detail the applicability of certain physical mechanisms to the objects under study, while the second makes it possible to determine general characteristics, like the rate of birth, the main paths of evolution, and so on. From an instrumental point of view, tools with a small field of view are more suitable for the first task, allowing you to achieve very high sensitivity and angular resolution. In modern X-ray astronomy, there are primarily the Maximum Newton and Chandra space observatories. The second tasks usually require survey observations. In the X-ray range, the most complete survey of the sky was performed by the German space observatory ROSAT. In this work, we study the observability of various types of isolated neutron stars using the eRosita telescope on board the spectrum-ranging gamma satellite. A detailed overview of this instrument was given by previous speakers. I'd like now to discuss the estimation of the eRosita dark signal level and detectability criterion. The SRG Observatory has an orbit located in the vicinity of the L2 Lagrange point of the Sun-Earth system. In survey mode, it scans the sky along great circles, rotating around an axis always directed to the Sun. Period of satellite rotation is 4 hours. Thus, a source located in the ecliptic plane will appear in the field of view of the telescope 6 times during the observations and leave 6 white bands in a frame, as shown in this figure. During the entire Fourier survey, at least 8 sets of observations of one object will be carried out. The number of observations of objects located in the medium ecliptic latitudes will be greater, and each such object will leave more bands in a frame during a single set. The band that a source will leave on the eRosita detector as a result of a single pass will have different widths at different distances from the center of the field of view. This is due to the fact that half-energy width significantly worsens with off-axis observations. Using an approximate expression for the width of the band, we calculated the area of such bands. Because of the variable width, one can select 3 circular areas of different diameters in the frame. The center of each area coincides with the center of the frame, and their radii are 10 means for a narrow field, 20 means for a medium field, and 30 means for a wide field. All these fields differ in the average image quality of the source and consequently in the effective signal-to-noise ratio. We calculated the average total level of the dark signal inside each area as shown here. Then, assuming that the dark noise statistics of the eRosita detector follow the Poisson distribution, we calculated the minimum detectable flux for an object located in the ecliptic plane with the minimum total exposure expected to be achieved in a full Fourier survey. We conclude that in the case of scanning mode, using of a narrow field only is the most effective. In this mode, the eRosita detector will be able to detect a source with a flux of at least 0.04 counts per second at the end of the Fourier survey. Therefore, we then take this value as a threshold value that determines the ability to detect and investigate a specific object. Let's now turn to the discussion of observability of specific types of objects. I will start with radio pulsars. Pulsars and rotating radio transients make up the most part of the population of known neutron stars. The ATNF catalog contains about 3,000 radio pulsars. We explore the possibility of detecting X-ray radiation from pulsars. To do this, we construct a spectral model of such radiation. We assume that a spectrum is the sum of thermal and power law parts. For thermal part, we estimated the internal temperature using this expression. Here T is a characteristic H. Further, we calculated the surface temperature. To normalize the power law part of the spectrum associated with non-thermal magnetospheric radiation, we use the X-ray luminosity, which is the sum of two parts presented here. We assume that the photon index of power law part is 1.7. Here you can see the formula for the resultant count rate. Let's move on to results of such modeling presented on these two graphs. The number of pulsars with a count rate greater than the threshold value is 87. The left graph is energy losses distance diagram for pulsars for which the dispersion measure is known. The right one shows the count rate versus the pulsar period. You can see that both classical and millisecond pulsars can be detectable. Now we will look at magnetars. Magnetars are young neutron stars with strong magnetic field. The McGill online magnetar catalog contains spectral characteristics for 30 magnetars related to the quiet phase of activity. We used this information to calculate the count rates for eRosita. For all of them, the count rates were quite high. We can expect that even in the quiet state of the sources, eRosita will be able to register 18 non-magnetars according to our detectability criterion. This table demonstrates spectrum models and the count rates for eRosita corresponding to these models. Moving on to the next slide, and the Magnificent Seven are close middle-aged isolated neutron stars with thermal radiation. All these objects were discovered by the Rosat satellite. As with other types of neutron stars, we investigated the observability of these objects using spectral parameters from literature. For all objects of this type, we used observed thermal spectra. And this table demonstrates the spectral parameters and simulation results. All the stars of the Magnificent Seven can be observed by eRosita. And finally, our last isolated neutron stars class. Central compact objects are sources of soft thermal X-ray radiation located close to the geometric center of the young supernova remnants. We investigated the possibility of observing CCO on eRosita using the method described previously. According to our detectability criterion, eRosita will be able to register 6 CCO. Spectral parameters and derived count rates for CCO are shown in this table. In our work, we not only investigated detectability of non-isolated neutron stars, but also explored search criteria. There are two basic approaches to the identification of new isolated neutron stars. The first implies cross-correlation, or using data from different instruments in different ranges of the spectrum. In particular, neutron stars can be distinguished by a high ratio of fluxes in the soft X-ray and optical ranges. The second is based only on X-ray data. Let us introduce the hardness ratio for eRosita. This value can be obtained quite easily from observations. However, it allows you to separate different classes of objects. In the figure here, we compare hardness ratio for different types of isolated neutron stars and active galactic nuclei. For AGNs, we performed hardness estimates for various redshift values under the assumption that the spectrum is absorbed power law with the photon spectrum index 1.9. For illustrative purposes, we fixed the count rate at a value equal to 0.04 counts per second, which corresponds to the limit of detectability based on the results of the survey. I would like to sum up the main points again. We concluded that in the case of scanning mode, using the narrow field only is the most effective. In this mode, eRosita will be able to detect a source with a flux of 0.04 counts per second. And the table here presents you different types of isolated neutron stars and the number of detectable objects according to our study. Also, we expect eRosita to be able to register accreting isolated neutron stars, as well as discover new cooling neutron stars and magnetars. Thank you for your attention. I'll be happy to answer your questions.
Thank you very much for this very, very interesting talk. So many details and on pulsar, on neutron star, and even on magnetars. Let's see if there are questions. No, there are no questions. But then we are very eager to look at the data. In particular, we have been active with Malenia and other people for a long time, and Orger in differentiating the nature of magnetars and the origin of magnetars, if possible to fit them with traditional rotating neutron star or even with the very massive white dwarf. Well, therefore, thank you again to give this opportunity to all of us, to all science, and congratulations again in the activity at Lomonosov University. Thank you.
Thank you very much. Goodbye.
Let's go now to the next talk, Shuang-Nan Zhang. Are you there, Nan Zhang?
Yeah, I'm here waiting to allow me to share my screen.
Beautiful.
Okay.
We will have this talk by Insight-HXMT, the first Chinese X-ray astronomy mission, and we have been following all through recent years your result, and please go ahead and tell us everything about.
Okay, thank you very much. I thank the organizers for inviting me to this very interesting meeting, and in particular, thank Remo and Gregory for the invitation. I'm going to show the highlights of the Insight-HXMT mission. And I think you'll notice I have some Chinese characters here. The reason is that Trump recently said, we all have to learn Chinese if Biden wins. Okay, let's start warming up. And this actually satellite is China's first actually satellite. It was selected in 2011. It's a 2.5-ton satellite. It's launched to a circular orbit at the height of 550 kilometers. It had several observational modes. It's designed for 4-year lifetime. It was launched a little more than 3 years ago. Then after the launch, it was dubbed at the Insight-HXMT. And the scientific objective can be summarized here. And we carry out the galactic plane scanning and the monitoring survey for weak transient sources in a very wide energy band. And we mostly make a pointed observation with high statistical study of bright sources with high cadence monitoring. And also, this is also Oscar monitor for Gamma bursts and the pulsars I will show you. So this is mostly in the MEV energy band. And here I show you the science payload on the satellite. And here we have the low energy instrument covering 1 to 15 keV with about 400 square centimeters. And here we have the medium energy instrument covering 5 to 30 keV energy band. Then in the center, we have a large array of sodium iodide. These scintillators covering 20 to 250 keV with 5,000 square centimeters. Here I show you, after considering all the effective areas of energy, from lower energy to medium energy and to high energy. And the main feature of the instrument is to have a large effective area in high energy band. And we have carried out, we have been repeatedly doing the galactic plane survey. The way we do that is that every time we choose a 20 by 20 degree field of view, then we scan through this area. And hopefully this will show up. The video doesn't show, but it's okay. So we go through each one by one, then eventually after about half a year, we have the coverage of the whole plane. And so far, we have gone through the galactic plane a few times and accumulated quite a lot of data. And this is it actually shows. Okay, so after about 1 year, that's the exposure map we have over the galactic plane. And this is one example. This is a scan through the galactic center region. It's one scan. You can see with the 3 instruments, it's in the low energy range because we have collimators that have different orientations. So different sources will go through the field at a different time and with a different response. Then we can use direct demodulation method to reconstruct the image of the galactic center region. Of course, only the bright sources can be seen, or the faint sources we do not see. So we are monitoring about 200 sources repeatedly. I gave you a couple of examples here. This is the very recent Euclidean neutron star over 7 to 40 keV band. You can see with the monitoring, we have a fairly good sampling of the light curve. Here I show you for Cygnus X1 is 3 energy band. The galactic plane survey, the monitoring light curve in this 3 energy band. So we are obtaining this repeatedly. And then I show you a few results from neutron stars. And one of the primary objectives is to detect the strong magnetic field of neutron stars through the so-called the cyclotron absorption line. Here you can see the long energy is related to the magnetic field in a unique way. Therefore, you can measure the magnetic field. This is one of the very first results from HXMT. Here, the data shows that the long energy from Hercules X1, it has been known over long term, has been decaying, and recently there's a possibility it reached a flattened evolution. And our data shows the detection of the line clearly. And with this data point, now the flattening is confirmed at more than 5 sigma significance level. And this work is done with the Tübingen group. You all know Rudy Starboard is an expert on doing the cyclotron study, and in particular on this particular source. Okay. So on another neutron star, this is GRO-J100857, we detected the highest energy from any neutron stars for the cyclotron line. It's 90 keV. You can see here the detection is very, very significant. This is with 1 detector module. And in fact, we have 17 modules. So we detected this line at more than 20 sigma. So therefore, it's really a very firm evidence for the very high energy cyclotron line from this neutron star. Therefore, the magnetic field it's reached to 10 to the 13. Gauss is the highest magnetic field directly measured. There's other indications of a stronger magnetic field, but this one is a direct measurement. Then for the Euclidean neutron star on the Euclidean geometry, and we also have some nice result here. This is one active burst from a neutron star. As you can see here, when the active burst happens in the hard active energy band, the flux decrease simultaneously. This effect was known previously, but by only adding many bursts together, you can see this. But here, with a single active burst, we now can see this deficit in hard active. So therefore, it tells us exactly what's going on here on the surface neutron star, and also how the active burst cools down the corona around the neutron star. And this from this Euclidean neutron star, Swift J0247. As you can see here, of a monitoring, of a very high cadence monitoring, have seen this almost entire outburst. And we have seen 2 transitions of the pulse profiles, and one is identified as the supercritical transition of the Euclidean disk, and this is one, and the other one corresponds to the super Eddington transition here, and both I should point out were predicted by Rashid Sunyaev in early 1970s. Now here we confirm this indeed happens, and we can see when this happens how the pulse profile changes. And also we have detected the QPOs changes simultaneously with these two transitions. Okay, so this work again, I emphasize we did this with a Tübingen group. And also, as you all know, that the kilohertz QPOs was one of the most important discovery of ART-E mission. But previously, this was mostly detected below 20 keV due to, we think, the effective area of ART-E. Now, in our high energy instrument above 20 keV, we see this double kilohertz QPOs very clearly. As you can see here, the RMS as function of energy, we securely detected above 20 keV. Now this tells us the origin of this kilohertz QPO is related to the non-thermal component of the radiation in this neutron star, and perhaps in other sources. And fast radio bursts, as you know, have been detected many times from all directions in the sky. But however, previously, not a single counterpart of the fast radio burst was detected, but the situation changed recently on April 28th this year, when the two radio telescope, CHEMI and STAR-2, detected here by CHEMI two very narrow fast radio bursts from the general direction of the magnetar, is from STAR-2, a single pulse here. And we detected the X-ray burst in a broad energy band from 1 keV all the way to above 200 keV, as you can see here, the X-ray outburst. And in particular, we see two narrow pulses in the X-ray light curve corresponding precisely to the two radio bursts here. So therefore, we securely identified the two radio bursts are associated with the two X-ray bursts, and generally with these large X-ray bursts, but in particular with these two narrow X-ray pulses in our data. And here you can also see the hardness evolution of the burst, and the hardness reached the peak near the time the two radio bursts were detected. We also have the capability to localize the X-ray burst. As you can see here, this is STAR-2 localization, and this is the CHEMI localization. And in the center, this is localization from our instrument. And clearly, our X-ray burst is, of course, within the CHEMI, the radio outburst, and in particular, and we have a smaller, much smaller error bar. So it's 3.7 arc minutes of the exact location, and with 10 arc second error. So therefore, we identify this X-ray burst indeed come from this particular magnetar HER 1935. And also the broadband energy, the lecture I showed you before here, and I show you here the spectral modeling over broad energy band, because we do have the capability over 1 to more than 200 keV. And you can see here the energy spectrum is best described with cutoff power law, with a cutoff energy about 84 keV, and also can also be modeled by a black body plus a power law. Both model the spectrum almost equally well, but we rejected a single power law model, and also rejected a double black model, which is the most popular model for magnetar's burst, and this describes the majority of the SGR burst. So clearly, this particular X-ray burst is very different from the regular X-ray burst from SGRs. So I finish the neutron star part. Now I quickly move on to black hole, and you all know that we have AGNs, we have active binaries that probe the gravity over the different curvature range, very large range. So we can study this, which complement the gravitational wave study. And to only show you a couple of results here, that is, we find the quasi-periodic oscillations over broad energy band, and this one shows over nearly up to 100 keV. But this one, for this max 1820, we have detected the quasi-periodic oscillation above 200 keV. This is so far the highest energy QPOs detected in any black hole active binaries, and the data quality is good. So therefore, we can also show the lag, that is the hard X-ray, the high energy with respect to low energy. As you can see, the high energy actually come later compared to the low energy photon. And the delay time can be very long, and nearly, you can see, it reaches very large radius. So we come up with a model to explain the result, because any radiative transfer would not produce such a large lag. And in particular, most of the radiative transfer model will produce hard lag, but here we see a soft lag. So therefore, we propose this is a jet, actually jet from the black hole and very close to black hole, and near the base of a jet, we have a high energy X-ray, and when you go out, you have a lower energy X-ray. Then the jet will precise this, and when this precision goes, we see gradually the hard X-ray and the soft X-ray and so on. So we reproduce the observed lag as a function of energy. And here we'll show you that the precision will produce the different lags as a function of energy. Okay? And also we found for the same source with the same data, we have the further evidence of the X-ray jet. This shows the evolution of shows the time lag as a function of the spectral index in different energy bands. This agrees with the early prediction in a model that for a jet, this phenomena should happen. Then again, I should emphasize this work was done with several European groups in Netherlands, in France, and in Italy, and in Southampton, of course, also with Tübingen people. We also observe gamma burst, and we can observe gamma burst over broad energy band all the way actually to up to 3 MeV. So this allows us possibly to constrain E-peak energy in a better way. Here I show you the effective area of HXMT, or in this middle energy range, MeV energy range, in comparison with all other gamma ray burst monitors. So clearly we have an advantage here in MeV energy range. So with this, we can constrain the spectrum of gamma ray burst better. As you can see, we show here a joint fitting of several gamma ray burst with the GBM instrument. This is GBM sodium iodide, this is GBM BGO, and we are in the middle. As you can see here, we do have more count here in the MeV energy range, therefore allows the better reconstruction of the spectral model. And since this Oscar monitor sees the sky all the time, so we are also monitoring all the MeV pulsars for Crab, of course. Every day, the monitoring can produce a pulse profile. And for other pulsars, this give you example for Vela pulsar in comparison with the Fermi, the high energy, and the CGRO-OC is 60 to 600 keV. Here, with over 380 days data, we see the pulse very clearly here. So we are monitoring several MeV pulsars over the time. And for gravitational wave counterpart, and you all know this is a very famous event, double neutron star merger. And we didn't see, we were observing this direction of the sky at the time, but we didn't see any signal. With that, we can constrain the spectral model about the MEV energy range. So therefore, our data also joined this multi-messenger paper. And to show you statistics, is not up to date, but it just shows you each month we are detecting several gamma bursts. Here, I just want to emphasize that we are detecting about 100 gamma bursts per year in the MEV energy range, and we are more in favor of a short gamma burst, because a quarter of our gamma bursts are actually short and hard gamma bursts. In comparison with the GBM, about 1/6 of the gamma bursts are short and hard. And we also played with the instrument to do something interesting, that is to use our detection of the Crab pulsar to do actual pulsar navigation. We achieved actually a reasonable accuracy with the 3 sigma, 10 kilometers localization of the spacecraft. So this is just something for fun, right? And the majority of our data are not available for download on our website. So if you are interested, you can come to download our data to do your own analysis. Most of the data are not publicly available. Here I gave you a summary of HXMT's over 3 years operation. This is the first accurate satellite with broad energy band in pointed mode and also monitoring observational mode. This is a small open observatory. We have a core program that is available, all the data available for all scientists working in China. And most of the data are not public. You can download. We also have a guest program. This program is open to the international community. So this is a worldwide guest observing program. This guest observing program is started, the AO3 starting August 1st, and we actually have a more guest observing time than the core program. And we also we are particularly interested in doing multi-wavelength observation. We have done this a lot with several spacecraft, and with also ground-based the optical radio and infrared telescope. So if you want to use our satellite to do multi-wavelength observations, we are very flexible to do that. Okay, so I just want to show you that I made a search on ADS just today, HXMT's paper. As you can see, over the past 3 years of publications, and both refereed paper and non-refereed, these are mostly GCA and ATEL. All these have been increasing very rapidly. Thank you very much. I will stop here if you have any questions.
Thank you very much, Nan Zhang. And let's see if we have questions. We don't have a question, but then I take this opportunity to congratulate you for this great mission. 163 GRB, 39 long, 39 short. This is quite a record, and you are participating in an essential way to the progress of this science, but as well to all the other beautiful results that you have shown. Congratulations, and let's keep in touch for further collaborations.
Okay, thank you very much, Remo.
Now we have Chluba.
I would need the screen sharing to be activated. Oh, perfect. So let's see. I hope this is working. People can see your screen. Can you see everything? Is my view in the way? I'm not so familiar with the software, unfortunately.
No, yes, that is perfectly okay. We can see you, and therefore we can start. What happens? Just a moment. Hello?
È caduta la sua connessione.
La mia?
No, quella dello speaker.
We have a problem with the connection of Chluba.
This could be just technical point. Okay, he's back.
Yeah, things crashed.
Okay, you're back.
I'm back.
We can-
Can you activate the screen sharing one more time? Excuse me, I apologize for this. Okay. Yeah, so it's a great pleasure for me to speak at this meeting, and I thank the organizers cordially to having given me the chance to speak here. I'm a little bit under the weather. My voice is a little bit crippled, but I hope it's going to be okay. So I'm going to speak about spectral distortions of the cosmic microwave background. It of course fits into the high energy physics regime as well, but it is in terms of topic, of course, a little bit different from X-ray observations. It is a topic that has been pioneered by work from Zeldovich and also, of course, Rashid Sunyaev. And I'm going to try to excite you about all the opportunities that might be waiting for us in the near future for studying spectral distortions. Okay, so the first thing to start with is, of course, the microwave background. And we all know that the observations of the CMB anisotropies have been a great source of information about the universe we live in. And this has been, an ongoing studies since many decades, and with outstanding success, we understand the universe and the main properties of the universe very well now because of these observations. However, there's a second piece of information, which is coming from the average spectrum of the microwave background. So the CMB temperature anisotropies, we're looking at the temperature in different directions of the sky, but we can also just study what is the energy distribution of the microwave background photons. And we all know, again, since Kobe-Firas, that it has been proven to very high precision that the average microwave background spectrum is very close to a black body of a temperature of 2.725 Kelvin. And this is a high confirmation of the Big Bang picture of the universe, the early phase of the universe. But there can be departures from this perfect black body. And these are usually described as mu and Y type distortions. When we're talking about spectral distortions, we're literally talking about those small, tiny departures from the microwave background average spectrum of a black body. So the mu and Y type distortions, they, as I mentioned already, go back to the pioneering works of Zeldovich and Sunyaev. And here's two figures illustrating the main types of spectral distortions. So the mu type distortion from the early universe, early phases of the universe, and the Y type distortion. The Y type distortion is also well known in connection with the Sunyaev-Zeldovich effect, of course. So clusters of galaxies upscattering CMB photons, and you're seeing a shadow in the low frequency part of the microwave background, and you see an increment of the flux in the high frequency part of the microwave background. This is one of the ways of studying clusters of galaxies, and it's basically looking at this hot X-ray gas but in the microwaves. So these two types of distortions, most important aspect is that the mu type distortion is something that is created through many interactions and scatterings, which is something you cannot achieve at the low redshift universe. So clusters of galaxies don't have enough scatterings occurring inside of them to actually push the spectrum to a mu type distortion. So you really can learn something about the early universe by looking at the mu type distortion. So let's put this into context. We have all seen this history of the universe in one or the other ways, starting with the Big Bang at early times, and then the universe cools and expands and cools. We have the creation of particles, BBN. We go through the recombination era, and then of course there's all the interesting things happen. Redshifts as well. The CMB anisotropies are sourced by the initial conditions set up, as we think, by inflation. By looking at the CMB anisotropies, we can indirectly infer, learn about these initial conditions. And then we have interesting things coming from the CMB polarization and secondary anisotropies that are generated at low redshifts. CMB spectral distortions, they cover, they teach you about the thermal history of the universe over a very wide range of redshifts, starting a few months after the Big Bang, redshifts of a few million to today. So if you have any type of energy release or injection of photons, which perturb the equilibrium between matter and radiation, you can create spectral distortions. And so this means that you're opening a new window to the early universe if you're looking at spectral distortions, in particular, a window to the pre-recombination universe. So the mu-type and Y-type distortions, you can think of them, the mu-type distortions really being a probe of the early universe, the pre-recombination era. I also added here the temperature era, which is basically nothing else than an era where thermalization processes are so rapid that you can restore a black body spectrum to a very high precision. So you're not talking really about distortions there. You're talking about just shifting the black body temperature. And then the Y-type distortions at late times from the upscattering of photons by hot electrons. And this is, of course, as I said, going back, this picture is going back to works of Sadovich and Sunyaev. And we now understand that there's a little bit more information because the temperature, the transitions between these three extremes are not absolutely are not instantaneous. There's a gradual transition between the mu and Y distortion era, and we can in principle think of time-dependent information being gleaned from measuring the spectrum in the intermediate regime. And there's also some interesting features introduced by recombining hydrogen and helium photons and how they actually cycle through atomic states in the pre-recombination and recombination universe. So this is all really very interesting, but from measurements of the microwave background with COBE, we know that the distortion limits are extremely tight. So there's no distortions, and just to highlight, the error bar on the measurements of the black body spectrum is covered by the thickness of the theoretical curve. So there's really no space for distortions according to COBE-FIRAS. However, we have, of course, very big motivations to think beyond COBE-FIRAS, because first of all, in the CMB anisotropies, we have learned and seen that there was amazing progress since the early days of COBE DMR, and then Planck, and of course, a WMAP in between, and also many, many ground-based experiments studying the cosmic microwave background anisotropies. But in the CMB spectral distortion regime, we're still basically 25 years in the past. We're still, the main limits are coming from COBE-FIRAS. However, people have been thinking about mission concepts that can in principle push these limits from COBE-FIRAS by several orders of magnitudes. One of the strawman missions that is one of the guiding ideas is PIXI, which has been proposed to NASA in 2011 and also in 2016 as a mid-X mission, which is a ballpark of $200 million, $300 million mission. And it had two main targets. One was to target the large-scale B-mode polarization signals, in principle reaching tensor to scalar ratios, which is one of the important targets of all the current ongoing CMB anisotropy studies. Tensor to scalar ratios of order 10⁻³ to probe inflationary physics, and then also to improve those long-standing limits from COBE-FIRAS by at least 3 orders of magnitudes. So the concept used for this is a Fourier transform spectrometer, which essentially really takes a Fourier transform of the sky in different frequencies. You have many, many spectral bands, several hundred, and you can cover a very wide range of frequencies to really study precisely foregrounds and separate these as well. So that's one of the ideas. Unfortunately, it hasn't gone forward, but very positive signs have been seen in the past in developments. First of all, it was recognized that measuring the spectrum of the CMB would be really one of the main targets for the next decades to come. And there is currently the ongoing NASA decadal review, which we also use as an opportunity to again highlight the excitement about spectral distortion science. There's ideas of measuring the spectrum from the ground. Here, one example called Apsara, which is led by some of my colleagues at the Raman Research Institute in India. And they are envisioning measuring at low frequencies, looking for the recombination lines. then there's exciting developments in the direction of measuring in the regime, in the higher frequency regime, the mu and Y-type distortions, led by the group in Italy, Paolo De Bernardis and Silvia Masi, and also Elia Battistelli, the Cosmo at Dome C concept. And this is no longer just fiction. It actually has received funding, and there's really starting to be, building of the cryostart and all these kind of things. So we are really looking forward to hopefully seeing some measurements and improved limits on the Y-type distortion, potentially reaching a factor of 10 or maybe even a little bit more, depending on how the atmospheric foreground handling can be done from this in the next years to come. We have started to really create a community being very, very interested in this topic. Here's a meeting that we organized at CERN together with Subodh Patil and Emma Di Mastrogiovanni, and many of the leading theorists and also experimentalists in this field have been coming together there. Rashid, very happy, and Subir Saka. Al Kogut should be sitting somewhere here. And then Joe was talking about the vision of thinking about going to the moon. That's one of the reasons why we have this picture of Donald Trump here in the back, because he is really thinking of pushing to go back to the moon. So there's lots of interesting developments in that direction happening over the past years. And we have many other activities. Pristine is one idea put forward to CNES, which is a small satellite mission. And Bruno Maffei is leading the BISU activity, which has now been going into the phase A. So we're really going to try and look at, studying what a balloon-borne experiment could be doing. And then I mentioned the decadal review submission, which we have done. And we have also last year used the opportunity to put forward white papers in connection with the Voyage 2050 activities, which is a big vision of the next 30, 40 years, 30 years of research up to the time frame of 2050. And spectral distortions have been one of the ideas which has been discussed there. And this is currently all under review. And we expect, with some delays, the report on this call to be generally submitted by sometime next year. And then last but not least, there's also Millimetron, which you guys have probably heard about. But at the moment, of course, Millimetron as a foldable 10-meter telescope in space with extremely high angular resolution and high sensitivity has many scientific opportunities waiting for it. And one of them could be spectral distortion measurements. It all depends on what kind of instrument is ultimately, or what combination of instruments will be on there. So this is all just saying there's lots of activity in terms of experimental pushing forward. Unfortunately, there is no measurements since COVID virus or real serious improvements on these limits, but there's lots of discussion going on. So this is really exciting. The other reason why thinking about spectral distortions is a quite timely problem, or a timely topic, is because there's many signals actually which should be there and which are waiting for us. So one of the, I here show a timeline as a function of redshift. And here up here you can see as the corresponding real cosmic time. The Y-type distortions are the late time distortions, and you have the mu and Y-type distortion transition in between, and you have here the high redshift universe, the temperature era. Then can you actually see the right part of my slide? I'm just confused about.
Yes.
Okay, very good. And then here on the right, I show several missions, and you can think of this whole slide in the vertical part as a sensitivity or signal level. So the missions that I mentioned, Pixie, and there's the Voyage 2050 and Super Pixie, they are having very high sensitivity, and then we have Phyros, which had the 25 years, 30 years ago sensitivities. So the first thing to think about is there are signals which are coming from the standard universe. These are guaranteed signals, and they should be there. clusters of galaxies at low redshifts, and we have the damping of acoustic modes signal, and then we have also the recombination lines and adiabatic cooling signals. These are guaranteed signals, and they should be there. We can, in principle, target them and really predict what kind of sensitivities we would need to measure these. And I will talk about what we learn from these signals in a second. But then one should not think about just these signals as you know, that's the only thing we can go for, because there's a huge discovery space. There's a lot of sensitivity signal space, which is not excluded by the measurements of Corby-Firas, and which could in principle contain lots of information about more exotic kind of interactions, for example, from decaying particles, black holes, axions, and paramagnetic magnetic fields. And also in general, the inflation paradigm could be tested in this way, because we know, of course, from CMB anisotropies measure at large scales, but there's also the small scale power spectrum, which we have predictions for if we assume standard inflation. So that's really exciting, and there's a big push in my group to study all these signals and what we can do with these signals. And we are also, of course, trying to motivate how to really go for these signals. So we're discussing a lot with the experimentalists and providing input to that discussion. So let's talk very briefly about what these different signals can be teaching us. And one of the largest signals coming from the low redshift universe during reionization and structure formation. So here's the signal as a function of frequency as we would be seeing it today. This is a Y-type distortion, so literally the Sunyaev-Selvidge effect, but on the average sky. It's basically the whole all sky stacked Sunyaev-Selvidge effect. And this is shown in absolute units. So this is the negative part of the Sunyaev-Selvidge effect, which has its zero crossing at 270 gigahertz. And then you have the positive part. So I mentioned the shadow in the CMB at low frequencies, and here the increments where you would see clusters as sources. But again, now this is the whole sky stacked. And here's a fiducial pixie sensitivity, just to tell you that this is a huge signal. And it can be in principle seen with a high signal to noise. And that means you can actually look for small corrections to the signal coming from relativistic corrections, because these clusters, they are hot, as we know from X-ray studies. They are several keV, and several keV electrons, they upscatter the CMB photons in a little bit different way than just in the non-relativistic calculation of the Sunyaev-Selvidge effect. And if you calculate the average sky correction to this, then you see that even this average sky relativistic correction, which has, you know, has the tendency of pushing photons a little bit higher and broadening the signal, this will be still very, very visible with a Pixie type experiment. This in principle allows us, I won't go into much detail, to study things about feedback models, which currently we're having, you know, from the simulation side, we're having a wide range of models, feedback models, which are in principle giving you the same viable results. But when you measure the temperature, the relativistic temperature correction, and the Y parameter of the average sky, you can actually pin down those models. And you can, in principle, even take a full census of all the hot gas in the universe, which even with future X-ray and SZ studies, we will probably only see of order 80% of all the sources really resolved. The rest is actually unresolved, so the diffuse SZ contributes. So that's all really interesting. But I think in terms of fundamental physics and early universe physics, the dissipation of acoustic modes is one of the exciting topics that can be studied with spectral distortions. And I just want to show here again the anisotropies that we have measured with Planck. And these anisotropies, they have been set up by inflation. And initially, we have, of course, seen you know, the inflation era setting up a quasi-scale invariant power spectrum, which we can now observe here as a damped version of this. So we can see that in the when we look at the power spectrum measured here by Planck, ACT, and SPT, that the small-scale power has been very strongly suppressed. If you undo this damping process, which is nothing else than silk damping, you can, in principle, understand that there was more energy stored in the initial state set up after inflation than there is presently available. So this dissipation of these acoustic perturbations is an energy release process, and the ideas of this go back, of course, to work of Jovic and Sunyaev in the 70s. So we can, in principle, by looking at the damping of these acoustic modes, we can study the primordial universe and the inflation process. And the physics is extremely simple. You just take black bodies of different temperatures. And if you take the average temperature, you would have a black body of this dashed line. Now, if you take them in a box and you just shake the box and mix up the black body to one uniform distribution function, without changing anything in the energy distribution of the photons or anything, just summing these two black bodies, you don't get a black body. And this excess of photons at high frequencies is in fact a Y-type distortion, which then thermalizes through thermalization processes to converts into a mu-type distortion, or if it is really happening very early, into a real temperature, average temperature shift. So this is the source of distortions just coming from summing black bodies of different temperatures. So physics is very, very simple. And this process has already, right after COBE virus, has been used, in fact, to put limits on the spectral index, because COBE virus, COBE DMR, was measuring the perturbations at very large scales. And with the virus information, you could in principle probe what is the amplitude of perturbations at small scales. Now, the limits were, of course, relatively weak on the Y parameter and the mu parameter of order 10 to minus 4, but nevertheless, that allows you to rule out that there's arbitrary power. So this is something that Wayne Hu and Douglas Scott and Joe Silk have been calculating, and based on these early ideas of Seldovich and Sunyaev. So this is really interesting. Virus has already, and it's not mentioned as much, has already put very, very strong constraints on the spectral index. We can now calculate this very, very precisely for what we know from Planck, using just a standard slow roll picture, and we would get a prediction of mu parameter of 2 times 10 to minus 8 plus or minus of order 5%, 10% uncertainty, just from the uncertainty of the standard of the parameters of the power spectrum that we have from Planck measurements. So the signal is down here. You can see with respect to the pixie sensitivity, this is already getting challenging. And if you actually look at the foreground challenge, you would see that pixie is not quite there to really see this, but there's now super pixie and potentially even things like Voyage 2050 that we're dreaming of. So this can teach you about the small scale power spectrum. And here's a figure just illustrating what we currently know in this direction. We have measurements at the large scales, and then we have several constraints in the very, very small scale power spectrum. Mind here the many orders of magnitudes of scales that are covered. These limits up here are rather uncertain because they depend a lot on assumptions about annihilating dark matter, etc., etc. Nevertheless, CMB spectral distortions will allow you to put more information and constraints on scales between 1 and 10 to the 4, a few times 10 to the 4 inverse megaparsecs. So these are very, very small scale perturbations, and you can put limits. In fact, the COBE virus limits would be living up here. So they, as I said, they already rule out power enhancement to arbitrarily, high levels at these small scales, superseding the limits that are existing, and also being the most robust limits still, I would claim. With Pixie, just the standard version of Pixie, we could push this down to nearly reach the level that we would predict from the standard slow roll picture. So this is really great, but we all know as well that people are discussing primordial black holes, all these kind of things, supermassive black holes, where do they come from? If there is indeed primordial black holes formed, then there should be enhanced power, and that means there's a transition, and we would be able to probe this transition. So this is really exciting and very, very interesting. I want to highlight, however, that there's, in addition to the scalar damping, which we all understand is just happening, as I said, due to silk damping. So you have a mode entering the horizon. Here's the scale factor, and it starts oscillating after being boosted by the potential to some level. And then when it hits the dissipation scale, it starts dissipating and losing its energy. That's the heating process that I already described. In a similar way, tensor modes actually heat and dissipate. But the heating here happens more in the free streaming regime, because tensor modes very, very weakly get damped by the interaction with photons. So they are basically a source of perturbations all the time, which means there's a driven oscillator in the universe, which is something we have worked out in detail with people mentioned down here. And this means that we can actually use spectral distortions to put constraints on tensor modes as well. So here's a figure that is an adaptation of a figure from a recent paper by Campetti and Komatsu and others, where they summarize the existing or potential constraints on gravitational waves from LIGHTBIRD, future measurements, and here also measurements with SKA, LISA, and other planned and envisioned missions. The interesting big gap here. And as we are now preparing with Andrea Merloni and Tom Kite, we are showing that this gap can be very, very strongly closed by spectral distortions. And in that way, of course, you would be really able to probe in very different scales. You would be able to probe things like phase transitions, axial inflation models, bubble collisions, interesting new physics that we are currently dreaming of getting a handle on. So I will be very brief on particle physics, which is another exciting domain where spectral distortions can be contributing extremely many things. We have even put a SNOMAS letter of intent in for a white paper writing, which will be happening in the next year in principle, because the SNOMAS community is really driven by particle physics. And so you can, in principle, probe decaying particles with spectral distortions. Here is a comparison on what is called the yield variable, basically telling you how much energy was released as a function of the lifetime of the particle in seconds. And here's existing constraints, again, FIRAS with very early constraints, and then measurements of the CMB anisotropies from a paper by Kawasaki. This is the latest updated constraint coming from Planck data, and this is very hard to improve because of astrophysical uncertainties, and spectral distortions could push this by a factor of at least 1 or 2 orders of magnitudes below this. And this means you can, in principle, measure directly the particle lifetime. And of course, in complementarity to the CMB anisotropies, you would be able to cover a wide range of particle lifetimes and particle abundances. So that's exciting. And then we can also look at interactions of dark matter with different standard model particles like protons, electrons, and photons. The dark matter, if it couples, extracts energy from the baryons, and this through the cooling of photons with the CMB leads to a spectral distortion which can be constrained. And here's just the predictions that as Yassin Ali Hamoud and Mark Kaminkowski and I did a couple of years back now, what a Pixie type experiment, still envisioning the old incarnation of Pixie, could be doing. And you can already see that this is in fact the only existing limit on interactions with protons and dark matter. And in particular with discussions like edges results in the 21 centimeter domain and the interaction of dark matter potentially with standard model particles. This is really exciting. And then there was also photon injection because of decaying particles. I won't go into details there. We have now a paper coming with Boris Boyer, which will be covering this in great detail. If I have 1 minute left, I would be just saying a few words about recombination, the recombination radiation. Perfect, thank you. And this is again a field that has been pioneered by work with Serdovic and of course Rashid and Vladimir Kurt, which pioneered the calculations of the recombination history, understanding the importance of the 2-photon decay rate, treating the Lyman alpha distortion from recombination lines, and then also later Viktor Dubrovich was of course pointing out that there's recombination lines coming from the high-level transitions and the recombination to the high levels. So we can now do these calculations very, very precisely. We have here a recombination spectrum with all the contributions from doubly ionized, singly ionized helium, and you can see as a function of frequency today, what would be the distortion level and the different transitions. This is really, really nice work, and Luke Hart is one of my students who's working actively on this. And of course, there has been many works in this direction with José Bartolo Martin and also Rashid, which we have been doing in the past, really pushing these calculations to a high level. We can now, on a standard laptop, calculate these things quickly, and in that way really do forecasts of what can we learn from the recombination radiation in the presence of foregrounds. And I point you here towards this paper which we recently put out with Luke Hart and Aditya Roti. So the recombination lines, they are smaller. You can see here, you probably need a factor of 10-ish more sensitivity. However, because of so many features, in fact, spectral distortions from the recombination era are not as inhibited or taking as big a hit as, for example, the mu distortion, which is a much more smooth, broad distortion. So this is something we can look at. And by looking at the recombination lines, we are probing at least 3 phases of the universe where these lines are coming from. And this means that if there's something non-standard happening between these phases or around these phases, we will actually see changes in the recombination lines. And in that way, learn extra time-dependent information. Here's a calculation that I did a couple of years back where I assumed there was a decaying particle, annihilating particle. And you can see that the recombination lines, the black line, the solid line is the without any annihilation. And here, if you have annihilation, you see that there's changes in the shapes of the lines, which means that you can learn something. So I will stop there, but just mention there's, of course, the big elephant in the room, which is CMB spectral distortion measurements are really hard. And there's foregrounds. And foregrounds are very difficult to handle, but a spectrometer like PIXI would be able to give you the coverage and frequency and sensitivity to actually do this. And I have in my team Mathieu Ramazet and also Aditya Roti, who are really both pushing the understanding of how we can actually extract these signals in the presence of realistic foregrounds. So I hope that we have been already trying to convince people that it's possible even in with realistic foregrounds. So I will stop there and say, spectral distortions are extremely exciting. There's opportunities waiting for us, maybe millimetron, super PIXI. There's pristine Cosmo and Bizou, and there's guaranteed signals, and we can learn something new. So I think this is really unique science coming for the next decades, and I hope that we will open this window to the early universe. Thank you.
Thank you very much for this very large overview and great perspective for the future. What happens? There is a message. Yes, there is Partha Sarati Majumdar was non-inflationary model may also account for CMB, Mu, and Y distortion. Could they, or is inflation essentially for virus observations?
Yeah, that's a very good question. And indeed, no, we don't need inflation as a slow roll, standard slow roll inflation paradigm. We don't need that picture to create spectral distortions. And this is one of the opportunities, because if we are just naively extrapolating our understanding of the universe at the larger scales with the CMB anisotropies, we would predict mu of 2 × 10⁻⁸. But if there's a different mu distortion present, then we know that something is going on. And because of the different time dependence of the injection processes, we're actually able to, in principle, distinguish the different sources of distortions as well. So if the universe is not, if the initial conditions are not set by standard slow roll inflation, but something else, so more broadly speaking, an early universe model, then we can also get mu distortions from this, and that would be one of the ways to rule out actually standard slow roll inflation.
Well,
or to test it further. Yeah.
Very exciting, and the new missions, and also I've seen the picture of Paolo De Bernardis and Silvia Masi. You are collaborating with, and of course, this of looking for new particles and possible injection in CMB is extremely exciting, and it's very nice to see your group in forefront of that research. Congratulations again.
Thank you. Thanks a lot.
Then with that, I think we have closed the morning session, and we have a break, and we will start again at 12:15.